All right. Okay, so we talked about oscillators a lot. We didn't talk about that. I don't think we talked about these problems yet. So, hence why you were asking probably. So I didn't read the questions. Well, I probably did. I just don't remember what they are. So
6.1 and 6.2 from chapter 6.
oh wait, no, this is last week, right?
Yeah,
Oh,
minus
assignment
8. Sorry.
Or no, you're right. You're on the right page. Solve problem 6.5 and 6.6.
Oh,
Yeah,
read
the first one
section
says read.
6.1.
Yeah.
6.5 and 6.6 at the end of chapter 6.
Oh, I see. Oh, okay. Damped. Good. Okay. Yeah, this is good. So I talked about this a little bit in the last office hours, but I didn't have a good. I didn't really have a good way to say it. So this is for springs in parallel and series. So I'll just talk about that. Have you ever heard of that before, like in a physics problem, putting springs in parallel and series?
Is it like an electrical circuit?
Yeah, kind of. You've heard of resistors in parallel and series, right? If you've taken physics too, I guess.
So my guess is parallel is where they're both together, but there's an object between them, and series is there's one spring, then there's another spring, then there's the object.
Yes.
All right.
I sort of forgot to visualize it while you're talking, but yes, I think that's right. Yeah. So if we have, we know. Okay. This is an object of mass m. Here's a k. That's I'll use little m. That's what everyone else uses. So we have an object of mass m, and we want to talk about the, now we could write this as a differential equation. We could do the whole story that we've been doing, which is, write it as F equals ma. F equals ma is always a differential equation, but in this particular case of a harmonic oscillator, it's a sort of interesting, I would call it non-trivial. You don't have to call it that. But anyway, a differential equation, and so because it's proportional, this force here is proportional to the distance, and so you have to do some methods to solve it, and we get the sine and cosine solution. So anyway, that's the whole story. I'm not going to obviously do that all again, but the story, the answer, looks kind of like this. I'll use sine. Of course, we could just use cosine. It would be the identical thing. We just have a different phase, right? It doesn't give us any different solutions. So here's what it looks like, and we know that omega, which is the frequency, I'll call it omega naught because I'm going to want to use, I'll call it omega naught for now. We know that omega naught has to be square root of k over m. And we know, the reason we know this is not random and it's not sort of trust me or anything. You literally can solve for this if you just use this test solution, just like when we normally solve a differential equation. We assume there's like a test solution with like a variable in it. And then we just plug it into the differential equation. We get literally this result, omega squared is k over m, and therefore this. So, of course, if it's negative, if you're worried about the negative square root, it doesn't really matter because of the, a negative sign. A negative number in here just makes it a negative sign, and then you just put in, it goes up and down, so it doesn't matter. Negative sign doesn't really matter. It could be like a phase shift as well. Anyway, so this is what we get. Now, now they're asking us about a resonant frequency. Okay. Now we could do this whole story with a damped harmonic oscillator, which is probably what they mean for us to say, because the only time they talk about resonant frequencies is with a damped oscillator. A damped oscillator is exactly the same, except, of course, so this is still review of like what we do. And there's a minus exponential kind of thing, and then there's like a sign. It looks kind of like this. This isn't exactly what, you could look in the book for the exact form, but it looks roughly like this. There's an amplitude, actually, there's an amplitude, there's a negative decaying exponential, and then there's an oscillating part. So this is the damped oscillator, okay? This is the undamped. Now, for this problem, it doesn't matter that it's damped at all. So I'm just going to, for now, just set the gamma to be 0, which means it's undamped, because, again, it doesn't actually matter for anything in this problem. Because we only care about it doesn't matter for anything in this problem. Because we only care about the actual oscillation part. The fact that it decays, and then the fact that the omega is a little bit different in the damped one doesn't actually really matter for this problem. But if we add another thing, which is the driven force, and I'll write it as F naught cosine, I'll just F naught cosine omega prime t, okay? I don't know what variable they use in the book for this, but it's another frequency. that they're driving the system at. In other words, they're applying a force, just like the spring force we could write on this mass. There's a damping force that we're ignoring for now, and then I'm just saying there's another driving force, and the reason it's a driving force is because it's oscillating. It has a new frequency. Yeah, did you want to say
So
something?
it looks like it's cosine. So for
Yeah. It doesn't matter for you're saying for yeah. That's what I was saying. It doesn't really matter
okay.
because we can replace the sign and just change this to pi over 2, and it's the same function.
Okay.
So that's why if I leave this phase here, it doesn't really matter.
Okay.
But anyway, so this is a driving force. It has a new frequency. Now, what's really important, which I've said at some point, but I was making a big deal of it, is that this omega naught is coming from the system. The system has to do with the mass and the spring. That you can't change this, right? Unless you can change the mass of the block, which we're assuming that like the system is fixed. But this is the driving force, driving frequency. We can probably change this. Like it's like an external thing so usually in a system like this is the thing we'd have control over because it's sort of an external force we're supplying. It's like another machine that shakes it back and forth. This is like built into the system, right? So we know that the amplitude, from the book and from, well, it's not from the book, it's from mathematics. But
You need some.
actually I just want to find a place to put this. That's fine. Okay. And we know from the book they tell us D, they read as D, this is just the amplitude now. And this is again for a damped oscillator, but it doesn't matter for our purposes. It looks kind of like this. And then there's something with a gamma. I keep saying I'm ignoring it and writing it, but this kind of doesn't matter for now. Okay? This is the amplitude, and I think they write it as a squiggle, in the function D this, something like this. Okay? This is the solution to a damped driven oscillator. It looks just like a damped oscillator. But and then of course we can ignore this for now. 0 just means I'm ignoring it. But the amplitude now has this other inverse term in it, right? And so resonance, this is how now I'm getting to what actual resonance is, when you can see that the amplitude is inversely dependent on the difference between these two. This is, again, the intrinsic frequency of the machine, of the device, and this is the frequency you're actually shaking it at externally in your applied force. As these approach each other, so as omega prime goes to omega naught, this D goes to infinity. Now, of course, if we had a damping force, it wouldn't go to infinity. But because if we ignore the damping, if we say there's no friction at all, and we drive it at exactly the frequency that it resonates itself at, we would get the amplitude would go to infinity. So this is resonance. Okay, so I know this is beyond what that exact problem was, but I'm just, summarizing this for now. Yeah, this is number
6.5.
6.5.
Oh.
It'll apply to both, I believe. Well, we'll see. I'll try to go over all of them specifically. Okay, so this is what resonance is. Now, all we actually needed, okay, so when they say what's the resonance frequency, they're saying is what's this omega prime such that it causes the amplitude to go to infinity. That just means, I know the answer. It's when omega prime is omega naught. So when they say resonant frequency, they're actually talking about omega naught. So I know that was like a lot of talking and stuff to just say that this is the resonant frequency. But it's just, I just wanted to, it's not completely obvious. It's not like this is not normally called, well, I guess you could call it the resonant frequency, but it's called that because it's the frequency that the driving force has to approach to get resonance. Does that make sense? So what I'm saying is that when they say resonant frequency, you should be thinking of this function. You don't always have to write it. And in this particular problem, you don't, of course, need to derive all this to get the answer. But I'm just letting you know when they say resonant frequency, they mean omega naught. Or if it's damped, it would be omega, which is like omega naught squared minus, gamma, 2 gamma omega, whatever. I forgot. It was on the last homework. It was some silly equation.
I gamma omega naught.
Yes, I gamma. Okay, so they were, okay, well, no, they use stupid notation. Okay, so I'm going to, Okay, I'm not even going to write it because their notation is not good and it doesn't match. But it's the one that if it was damped, it would have this minus something.
So the I is an imaginary number. Omega naught is omega naught.
Omega naught is, well, you know what? I don't even know.
According to this notation right here. But what exactly is gamma in this case?
Gamma is this, defined with the damp. So if it had a damping force,
But it still has gamma here.
yeah, well, it should have gamma if it's damped.
No, I mean, like, what exactly is gamma? Is it just some constant that
Gamma's a
depends
constant.
on the...
Yeah, so the damping force is defined as something times velocity. So remember in the baseball problem, we had the damping force was like v squared, right? In this case, they're just saying it's times v, and there's a reason, the mathematical reason they're saying this. It's not a physics reason. Because you might think, well, why did we use v squared before and now we use v? The only reason is because they're both fine approximations for damping, and it's actually really hard to solve with v squared. Because they need v to keep it as what's called a linear differential equation. So if you want to look up nonlinear differential equations, please, and don't tell me about it because they're really hard. But that's why they use v. Anyway, but of course, for the coefficient, they could just use like a letter b. But when you solve the differential equation, you end up dividing this by m, so they could just define.
So it's just a constant, it's dimensionless?
It's not dimensionless, but it is a constant.
Okay, so it's just a constant and applies to any problem, or does it depend on the spring? Does it depend on the circumstances?
It depends. Well, this statement is fine. Actually, it's minus. This statement is fine on its own as it's just a damping force. Yeah. Gamma would have dimensions of, well, you could solve for the dimensions. You have newtons over kilograms, so it'd be like meters per second squared. Divided by meters per second would be like 1 over seconds or something. So that's fine. That's the units. It depends on whatever the cause is causing the damping.
All right, so
if it's like if you put this whole thing underwater, and you had to like oscillate a spring underwater, you might have a damping force like this. So omega would just depend on the water.
okay, so it's one of those things where you'd either have to solve for it or you just have to look it up.
Yeah, I mean you shouldn't. Yeah, I mean you could solve for it. I would treat it like just one of your inputs, just like the mass.
Okay.
You could solve for the mass. In most problems, we're okay with leaving the mass in there because we know that if you wanted to really do it, that's where you put the mass. This is the same. Think of this just like the mass. It's just one of the inputs. It's also like F naught. Like, I don't know, you just find out what the force is and just put it in. You know what I mean? Like, just treat it as it's a fine variable to leave in your whole thing. It's just, yeah, again, it's just like the mass or the spring constant. Yeah, I think you said that, so yeah. You're right.
Okay.
Anyway, so we have omega or omega prime, whatever it's actually oscillating at, that's the resonant frequency. So now I totally forgot what the problem was. I just remember it said resonant frequency, but effects of, oh.
He might be meeting with his group.
Oh, okay, good. Sorry. You're right. Oh yeah, you're right, parallel and series. So, okay. Well, we know that this is the resonant frequency. They're asking how this changes. Now I'm going to do undamped because with damped it actually doesn't really matter that much. I mean, again, you should just plug in the equation they give you, and I think it won't really. The effect will still be the same whether it goes up or down. And so now all we need to find is, well, if you put springs, if you modify this system so that the springs are in series or parallel, m is not going to change, but of course k is. So this problem reduces to, so we had a bunch of words that had to do with oscillations, and we've reduced it to what is k of two springs in parallel and series. Right? So this is what so does everyone kind of see what I'm talking about here? I'm just saying that we read a problem. It seemed to have a lot to do with oscillations and frequencies and stuff. And we've reduced it to, as long as we can answer this question, what is the k of two springs in series and parallel, we should just be able to plug it in here and find omega naught, and omega naught is the resonant frequency. So I'm just trying to reduce this to a problem that we haven't done before. Reduce this to a problem that's not just renaming things, because everything else so far is renaming. So that's what we need to find. Now, this is actually kind of an interesting problem. This has nothing to do with oscillations or waves or anything. But it's actually kind of interesting, so I'm going to erase all this for now. And erase all this and just write this is just a separate problem. You could do this for any, like they could have asked you how to do this in, just as like a force problem. You don't need to do oscillations for this. But let's say you had two springs in parallel, K1 and K2. Okay, so that's parallel, and then this is going to be series. Okay, so parallel and series, by the way, are of course names from circuits, and it just means, of course, you have two resistors in the same line of a circuit. Those are going to be in series, and if you have them as two alternate paths connecting 2 points, those are in parallel with each other. So anyway, in case you've never seen, if you've seen those before, it's essentially the same idea, and we're going to see that. Remember, well, there was a little thing. There's a section that he told you to skim, which probably means don't even read it at all. But there was a little section, chapter, it's like 6.3 or whatever, it was about RLC circuits. And it was basically about how the differential equation for a damped harmonic oscillator is identical to the differential equation for what's called an RLC circuit, which has an inductor, L, a resistor, and a capacitor. And if you write the charge as a differential equation, where the charge is, those literally have a one-to-one correspondence with the voltage and the force are exactly equivalent. And if you just do one-to-one correspondence, you get the exact equation for the charge is differential equation, and it's the same solutions. So you can kind of see why they're talking about series and parallel, because just like in circuits, you can add things in series and parallel. You can do that in these too. And so, okay, well, if we want to find, let's do series. Well, if this distance here, so what I want, what's the definition of the spring constant? If I apply a force, okay, how much x does it move? That's the definition of the spring constant, right? If I apply a force in this direction, how much x is moving? I'm not going to worry about minus signs for now. Just pretend I'm taking the absolute value of everything. Of course, f and x are always opposite directions. Otherwise, it's not a spring. But I'll just pretend that f means absolute value and x means absolute value. That's fine. So if I apply a force to this block, right? Well, let's say if I apply a force here, okay, this is series. Then K1, well, how can I define, what's K1 equal to? Well, K1 must be equal to F1 over X1, right? This is just, again, I'm just writing what for this one spring. X1 is just the amount that this changes by. And of course, K2 is the same as F2 over X2. Now, the key point here is that F1 and F2, they're acted on by the same force, right? The force acts on both of the springs. So F1 and F2 are the same. So I could write them as the same, but the other thing is that this x here, the total x, must be equal to x1 plus x2, right? In other words, if I compress the whole thing by distance x, I can say that spring 1 compressed x1 is spring 2 compressed x2. Well, x1 plus x2 must be x, right? And x really should be the change in the position, whatever. And now, I want to write, so now I guess I could move these both over, so I get like f equals
you want to get x over.
Yes, you're right. Yes, I want to get x here. So this, okay, so x2, yeah, you're right. So f over, and this is going to be f, yeah, okay. So x1, sorry, I should have written it like this. Okay, this is this, of course, these are still true, but this is a better way, yeah, thank you. There's a better way to say, so now x1 I can replace with this. So this is this, and x2 is, there we go. And now I can divide the top and bottom by f, right? That's just a, you can always do that. 1 over, divide by f is 1 over k1, 1 over k2. So I've shown that k, and I'll write it as k eq, for, that's the same thing we write in circuits, right? Equivalent spring constant, is this. And so Now this looks a little weird because there's multiple fractions, so you could also write this as KEQ inverse is K1 inverse plus K2 inverse. Right, now this looks just like for resistors, right, in parallel actually. Or capacitors in series, which is actually, if you do the thing I said with you change the differential equation for the oscillator to the circuit one, every single variable, of course, has to map to every single variable in a spring system has to map to a one in the circuit. And in this case, the K actually maps to the spring, or it maps to the capacitance. So this is the reason why. Well, that's not one. That's another explanation of why this is the case. Anyway, and now if you know about circuits, you'll probably guess what the other one's going to be parallel, but we'll do it. It's actually really simple. It's just that so this is parallel now. Should organize this board a little better, and in parallel, well, we get that if you apply a force on it, so K is going to be KEQ now. Is going to be, if you apply a force on it, it moves the distance x, but of course, you have to move both of them that way, right? Like in other words, if you compress this a distance x, you have to compress both of them, and so essentially the force you'll get is going to be the sum of the individual forces like this, and so you'll get F is really, you could write it as F1 plus F2, right? And X is constant, and F1 is K1X, and F2 is K2X, right?
Since it says that both springs are of an equal spring coefficient, that just means that we could just double everything, right?
Yes.
Okay.
Well, you have to be careful. So in this case, we could plug in just K1 for both, and you would get something simpler.
Okay.
But we can't, but I just want to do it in the general case, whatever. So you get that the force you apply is going to be equal to the sum of the two forces, and so this is K1 plus K2X, right? I can factor out an X, and it's important that X is all the same, and therefore you get that the spring constant in parallel is just the sum of the two spring constants. Now this is sort of very intuitive, because if you imagine, well, if I take a spring and it has some, like K is like the stiffness, right? So how much force does it take to compress the spring? If you add another spring, if that's really, really easy to compress, you're only going to make it a little harder, right? You're going to make it some amount harder because you have to do both things at the same time. You have to compress the original spring and another one. Whereas in series, well, here's the fact about this equation is that this number is always less than either of these numbers. KQ is always less than K1 or K2. That's just a fact about this type of equation. And that just means that whenever you stack springs like this, it's always easier to compress than either one separately. Right? So that's what this equation is telling us. And it's actually kind of intuitive, because if you imagine, well, if I take a really stiff spring, it's really hard to stretch, and I put a really loose one next to it, it's always going to be easier. But if I take an easy one, it's already easy, and I put a really stiff one, it's still going to be easier because I could still stretch the original one, and I could stretch a little bit of the stiff one, right? Like you can try to come up with situations where it wouldn't be easier, but you always get, when you stack springs, it's always easier than either one individually. And easier to stretch means a lower spring constant, right? Spring constant is like the stiffness. So anyway, okay, so that's all that. Now, of course, if they say it's equal, that's just a simpler case. This is just going to be 2K, and then we could kind of solve for this, and we get, 2 over K, and then we get so in this case, we'll get KEQ is 1 over 2 over K, which is going to be K over 2. So it's actually half. So, which again kind of makes sense, because if you're saying, if I have one spring and I stretch it and it costs some force for me to stretch it a certain amount, if I have two of them stacked, to stretch it that same amount, well, each one only has to stretch half as much, because there's two of them. So it's actually, right? If I wanted to stretch it, I could stretch it actually double the distance, because there's just two in a row, right? So each one costs some amount of force. So if I stretch it double the distance, it's the same amount of force, and that's K over 2. Anyway, so I think this is actually pretty intuitive, but well, this statement might not be, but anyway, so that's springs. So once we have this, here we can just plug it in for omega naught. So if they said, okay, you have one frequency for a spring, and now you just add another spring in parallel with it, what happens to this? Well, this will go to, K will go to 2K over M, and so we've got an omega naught goes to radical 2 omega naught. So it gets higher, right? It gets faster, which makes sense because a very stiff spring is going to have to oscillate very quickly, right? Because there's a lot of forces on it. So it's going to oscillate very quickly, and so if you put the springs in parallel, you're actually adding more stiffness to the system, and so it's going to want to oscillate more quickly. This better be the opposite because we know that if you stack the springs in series, it's easier. There's less force on it because it's easier to oscillate, and so there shouldn't be as much of a restoring force, and so it shouldn't oscillate as quickly. And we see that if we replace this with K over 2, that omega naught goes to omega naught over radical 2. It's the same thing. You just put a 2 at the bottom. That's if they're identical. Of course, if they're not identical, it's a little more complicated. But the principle is always true that it's always less when you put them in series because you're decreasing your spring constant. You're decreasing the forces, so you're decreasing acceleration, and so you're not having as fast of an oscillation.
Okay. And if it says mass is doubled, then all we have to do is, it's basically the same as if it's in series, right?
Yeah. Right. You just change M to.
Okay, so
yeah.
The answer is the same for part B and part C.
Yeah, if it says series, yeah.
Okay.
Does that make sense?
Yep.
This would be I'm only saying this to you because I said this to the last office hours people, that this would be a really good question for like a quiz. I'm not saying that because I have any information. I promise you, I literally have no idea. I'm just saying this is actually kind of a cool little problem because it's like you don't need to know anything beyond this, but yet it's kind of like putting things together the right way is kind of an interesting little problem. So
Okay. Just to be sure, I
Yeah.
understand what you're saying and what you're not saying.
Uh-huh.
Blink twice if you
I-
think this is going to be.
I literally don't even know I know everything's on Blackboard that I can see is for your homeworks and the project, but I have there's no quizzes on there. I don't even grade them. Like he does all the quizzes, so.
I think those were 2 blinks. What do you think, Joe?
If you take the first letter of every word I said, you should spell out something.
Spell something.
So anyway, I really don't know. I'm just saying. I'm just saying like
If you were in
Don't-
charge.
I don't want you to. If I was in charge, but I don't want you to think this is all waste of time just to get. Okay, it's radical 2, great.
Okay.
Or like, I don't want you to think, oh, in parallel, it's probably going to be like doubled because most things when they ask questions like this are doubled, and therefore it's like radical 2. That's a very common answer. So I don't want you to think this is all like a waste of time just to get to the answer. This is actually an interesting. Some things are wastes of time to get to the answer. That's actually happens a lot.
You'll let us know when it's a waste of time, right?
Oh no, yeah, I would totally
Okay.
do. I would say that you don't need to know this and that. I don't know if you explicitly know how to do this problem. I wouldn't memorize how to do this problem, certainly. I wouldn't memorize how to do anything. But I really like this problem because it's kind of a clever little thing. It's also on Wikipedia. If you want to see a better thing, if you literally do Google like Wikipedia springs in series and parallel, there's like a little derivation that's identical to this that's written better.
Let's try number 6.
Okay. Yeah. Oh, does anyone have any questions about this left? Or okay. So number 6 was about.
A damped harmonic oscillator.
Yeah.
Is this a waste of time?
Well,
I have questions on
on number 6.
Yeah.
Well. Yeah. So okay. So I'm not going to put in the numbers.
it.
I
Okay.
hope that doesn't bother you.
No,
Because the thing is, if I put in the numbers, I promise you I will get confused and I will do something wrong.
that's yeah.
So I don't want to do it. So if you're getting weird numbers, maybe I don't know if you're already trying it without the numbers, but of course they give you numbers so that you put them in. But I think that's a bad idea. So I'll just go over it and then you can tell me if this helps anything. But yeah, so they want you to like practice plugging in things to this equation because they want you to kind of get used to the damped oscillator. And So they give you M, they give you K, they give you the damping force, but they want you to solve, so the first part is they want you to solve for alpha. Oh, I see, but they, okay. So let me just write the differential equation again, because that's where all these variables are coming from. So this is MA equals the sum of the forces, which is going to be minus KX, so they told us K. FD, oh, that's it, it's just FD. And then they say FD is, well, I'll say plus FD, and FD is minus M alpha V, which is, of course, the same as, and then in somewhere in there they say, he says in the homework description, like, it's the same as gamma. So just don't get, it's the same, because it's identical to the way they've written gamma in the book. I'll just keep saying alpha because that's what it says here, but. Okay, and now then we could write the solution, because we know the solution in terms of these things. Well, actually, can I see this real quick? So let's just write exactly what they have for a damped oscillator, which is, okay, so it's dE to the minus gamma t over 2. This is 6.6, equation 6.6. I'm just writing the answer because, sorry, it should be alpha, I guess, times cosine of radical k over m minus gamma squared over 4 times t plus, I think they use delta for the phase. They use like, yeah, they use delta. I kept writing phi for the phase. It's the same thing again. It's just, you know, I gotta just pick the one they use, but of course sometimes they do a silly thing. But so the reason, so at equation 6.4 is the actual differential equation, and equation 6.6 is this. I'm not solving it because they've already done it, and why would we do it again? So let's just, we're just gonna copy this. Now, of course, sorry, this should be an alpha. Now they ask us to find alpha. Well, do we have actually enough information just from that, from what I said? Of course, there's another line about the decaying. We actually don't, of course, have enough information, because if I put any alpha, this equation solves this differential equation. Right? If I plug this in here, this equation solves this for any alpha. So of course, we don't actually have enough information here. But what they say is that the initial amplitude is 20. So I'll say A0 is 20 centimeters. Now I'm not going to ever plug in this 20, and you'll see actually why it doesn't even matter. But and it falls to half after 6 oscillations. So A after 6 oscillations is 10. Now you have to find the damping coefficient and the energy lost. Okay, this is kind of fun. So now if you've ever done any problems, and again, if you've, I don't know what class this is in. It might be physics 2, but you might not have taken physics 2, or you might not have even covered it. But this is like exactly like a half-life problem. So if you've done any problems in like chemistry, maybe even about half-life, this will reduce to that. Now, of course, it's not obviously that. We have to do a little bit of work, but so remember, the amplitude is just the part. The amplitude is for a wave, right? The wave is this part, right? This whole thing isn't the wave. It's just this part right here. So this quantity, dE to the minus alpha t over 2 is the amplitude of the wave. So when they say the amplitude is decreasing, which is, because remember, this looks like this, right? It looks like this, and this plot, and also the negative version, but this plot is dE to the minus alpha t over 2. So that's how this works, because this is an oscillating wave, has an amplitude of 1. A cosine of anything has an amplitude of 1, of course, it's sort of sine. But it's multiplied by something that changes over time in size. And so we can draw this actually pretty easily without having to like plot anything. We can draw this because it's just this wave function, oscillating function, bounded with an amplitude that decreases over time. The amplitude is given by this function, which if we just plot it, we'll just draw a bouncy little line between it, and that's literally this function is identical to this. Now, of course, we have to worry a little bit about the phase, but I don't care about that. So, okay. So we know the amplitude is actually this thing here. So when they say the amplitude decreases, we don't actually need to know anything about this wave. So let's say at 6 oscillations, that happens at a time. I'll write it as a time tau. I don't want to write t because we have t's as variables. Actually, yeah, I'll write it as tau. Not to introduce more Greek letters.
What's that? 6 oscillations.
6 oscillations, yeah. That I'm just labeling with the. So I'm going to call it a time tau. Tau is the time when it happens 6 oscillations. Now, we're not going to solve for that right now. But if I know that the amplitude is always given by d e to the minus alpha t over 2. Now, at 0 time, it said it was 20 centimeters, right? And I'm just going to call this A naught. Okay? And when it's at this point, it's actually half of that. So I'm just going to call this A naught over 2. Okay? Now, if you want to plug in numbers, you're free to. You will see that this specific number actually doesn't even matter to the answer. It could start at any point, as long as they say half. That's what matters. So at t equals 0, the amplitude is, of course, just A naught, right? Which, of course, if we plug in 0, it adds up being d. So we could replace d with A naught, but I'm not going to do that for now. And then they say at some time later, it should be A naught over 2. And so actually, I am going to do that, sorry. I am going to replace this with A naught. So this is the actual equation, because at t equals 0, this is satisfied, right? So the amplitude, really, I should say d at t equals 0 is A naught, but whatever. Now, the amplitude is A naught over 2. Sorry. What am I lost my train of thought. E to the minus alpha tau over 2 is A naught over 2. This is the expression for the amplitude at a time tau. If I plug in any time, it should work, right? And I'm setting it equal to A naught over 2. Now I can solve for tau, right? So if I take, how do I solve for tau? A naught cancels, and this is why I said it doesn't matter. If I plug in 20, we just cancel. And you get e to the minus alpha tau over 2 is 1/2, right? Take the log of both sides, and you get minus alpha tau over 2 is, it's going to be log of 1/2, which is actually minus log of 2 by log rules of negative exponentials. And you can put the plus sign on both, and then you can solve for tau. Well, actually, sorry, we actually want to solve for alpha, right? Forgot what the problem was. And you get 2 ln of 2 over tau.
This was from equation 6.6, right?
Yeah. I'm using just the amplitude.
Where's tau in this?
Tau is a time. Tau is the time of just any time. It's actually going to be the time when the amplitude is half, which is sometimes called the half-life. Of course, in this little thing I've written here, we didn't use anything about the fact that it was a wave. We only used something decaying, and that's because that's all that matters. For the amplitude isn't oscillating. The amplitude is just a number that decays. The wave is oscillating, but again, so this is another important part of these big equations you're going to see, and of course, for most problems, you don't need to use the entire equation. You only need to use a part of it. So anyway, so this is a very common half-life formula. Sometimes they don't have the 2 here because they don't have a 2 here sometimes. But anyway, you'll see this a lot if you do like radioactive decay as it happens. With this log of 2 comes up. And it just has to do with, the half-life of, because of course the amplitude is never going to go to 0, so you can't just say, oh, well, how long does it take to go away? Well, it never goes away, right? This number is never 0. If you set this equal to 0, you can't solve it. There's no time that it equals 0, right? Whereas you can find the time when it goes to half of whatever it was. And it doesn't matter when you start that. You could start that at any point. The time between that point and when it's half is always this constant number. That's just how exponentials work. Anyway. And now of course, all we need to do now is find tau. And tau, remember, was the time of 6 oscillations. Once we plug in tau, this is a number. 2 ln 2 is a number. ln 2 is like 0.6 something, 0.6904. That's probably not right. But anyway, you could look it up. Times 2 is whatever, and then over tau, right? So does that make sense? So we've reduced this to all we need to do is find tau, and then remember tau was just the time. Tau is time for 6 oscillations, right?
I thought T was for, at 6 oscillations, the initial amplitude is equal to 1/2, right? Okay, so
The amplitude is equal to half of the
okay,
amplitude at
okay.
t equals 0.
Okay, I understand.
So I just skipped. I mean, you could have done this part first. That's also fine. I just want to do this first because this is the interesting part. This is the new part, basically. This is the other one is, well, we have a frequency here, right? Now we need to talk about the wave. So now this part, this tau, is asking us about the wave. It's not asking us at all about the amplitude anymore. So again, this is just the overall point, is that you see these big equations and you think, I don't understand every single part of it, I can't do the problem. In this case, we actually only needed parts of it separately. So for the tau for 6 oscillations, which I call tau, this is the frequency omega, and well, 6 oscillations is actually, if we find the period, t is the period, which is the time for 1 oscillation, right? So of course tau is 6t, right? And so all we need now is to find t. The way I'm writing these on the board makes no sense, so just hopefully you can follow the route I'm taking. And now t is, well, it's 1 over the frequency by definition, but this is not the angular frequency. And f, so here's where you have to like remember a bunch of stuff that I usually forget. I think it's this, so it's like 2 pi over omega. Pretty sure that's right. So t is 1 over the f frequency. This is just the Hertz frequency, not the angular radian frequency. And f is omega. Is that right? Yeah, it is right, because this is, let's check units. And remember, I always say radians aren't really units. That's true, but sometimes they are. They're not units, they're labels. Like, it's kind of like revolutions. 5 revolutions doesn't really have any units, but you should kind of keep in mind that it's revolutions, because it's not radians. That would be a different number. So omega is in radians per second, and 2 pi, again, this is where it seems like it doesn't have units, but it kind of does. It's actually the number of radians per revolution. And so these cancel, and we get revolutions per second, because there's 1 over seconds and 1 over revolutions. So we have to like invert the whole, it's like a, whatever. So we get revolutions per second, which is exactly what F is. Because when we say, really, when I say Hertz, that really means, Hertz literally means 1 over seconds, but revolutions per second is kind of the same thing. So this is right. So it's this, because this is very common, for at least for me, is I forget where the 2 pi goes. Does it go, is it 2 pi omega, is it right? But if you put like 2 pi omega, you would know that 2 pi, it's always 2 pi radians, right? That's the only time you'd ever use 2 pi is when it's radians. And if omega is in radians, you have like a radian squared, and that's not good, right? You want them to cancel. So anyway.
It also tells you on page 105 in chapter
It also tells you.
7.
Okay.
So
It says on page 105 in chapter 7. So yes, those things, it's worth it to, I hate saying the word memorize, but like remember that those are all there. Because if you're in the world of tau, if you're in the world of t with periods and frequencies, and you completely forgot how to go to the world of radians, you're sort of going to be stuck because I don't know how to take anything from this and make it into revolutions, right? Or cycles or whatever they call it.
So we want to be fluent in both radians and cycles, revolutions?
And at least have remember one that relates to you. I mean, you don't even need to remember it. You just need to know that frequency is frequency. They're both frequencies. And there's a 2 pi somewhere, because one of them's in radians and one of them's in cycles.
All right. So it's
Which
just
is 2 pi radians.
So it's just a conversion, like Fahrenheit to Celsius. or
Exactly.
Meters to feet.
Exactly. It's just a conversion, but of course you can't just be like, well, they just differ by a factor of 2 pi. It's like,
Okay.
well, where does it go? So you need to remember which is which. But again, as I said, 2 pi, a way to remember is that 2 pi is always 2 pi radians per something.
2 pi is always 2 pi radians.
Yeah, because like, why else would you use 2? It's not, you're never going to say, how long does it take to go to 2 pi times around?
Okay.
That doesn't make any sense. So it's always 2 pi radians, and so because we want to cancel the radians up here, omega is of course in radians, so we should put the 2 pi on the bottom to cancel it, because this thing doesn't want any radians.
Okay.
That's just I like the units I did here. These are sort of fake units, some of them. Seconds is not, but radians and revolutions are kind of fake units. I shouldn't say revolutions, I should say cycles. Because as we've seen, a cycle is just when it goes around 2 pi radians, right? A revolution is if this was all like a spinning thing. You could, of course, talk about all this in terms of, like, you could do rotating systems just the same exact way we've been doing them. But I'm just pretending, of course, nothing's actually rotating in physics, in real world. It's just sort of rotating in the angle plane kind of thing. Anyway.
So what about the energy lost during the first 6 oscillations?
Yes, so that's a good, so the energy is going to be, I don't have any room, but, so the energy is always, I'll erase this. The energy from an oscillator, now, if you know, we could of course talk about the kinetic energy sometimes, and we could find that by taking the time derivative of this and finding the velocity. That's not a lot of fun at all. Don't do that. That's a horrible idea. It will be completely correct, of course, if you want to take the time derivative and find the velocity and then do 1/2 k mv squared. This is not fun. This has 2 terms. You have to use the product rule, and then you have to. No, don't do it. So what you can do is just say, well, it's oscillating. I just want to pick the points when it's all in potential energy, and the potential energy is only due to this spring, right? There's a drag force, but when it's at the top amplitude, like if it's at the maximum sort of highest compression of the spring, it's not moving, and so none of the energy is going towards the work of the, you know.
So in that case, couldn't we just take the potential energy when amplitude is in the beginning, when amplitude is equal to 20 centimeters, and then take the potential energy at the very end of the last oscillation, the 6th oscillation, when amplitude is equal to 10 centimeters?
Yes.
And just take the difference?
And that's exactly how you do it. That's exactly how you do it, but actually, wait, do they say after?
It says the energy lost during the first 6 oscillations.
Oh, okay, well that's easy.
So yeah, so it's just
That's
initial
stupid.
minus
Okay,
final.
I thought it was going to be more interesting than that, yeah.
Sorry,
So-
it's a disappointment.
No, you're exactly, you helped me, because I was going to tell you how to do it algebraically, which is just, yeah, so of course they told you the amplitudes. They told you it was 20 and they told you it was 10. This is, sorry, this has a squared, I forgot the squared, just make sure you write it. Squared. This is the potential energy of a spring. If you want to know where you get that from, it's just the integral of the force of the spring, which is kx. So anyway,
Okay.
so by the whatever work energy theorem, whatever it's called. So this, and x is the position, but of course, if we're talking about all the energy being in potential, which is the only time we want to use this is when all the energy is potential, right? When we want to call it the total energy, I can write this as total energy is this when this is the amplitude, right? And of course, the amplitude at time 0, which is the first point, is when the amplitude is 20 centimeters, so just plug in 20, and at the end, I'll call it the end. I just mean when it's after 6 oscillations. We know it's a over 2. Of course, they told you the number, it's 10, but we can just make sure, by the way, when you have to convert it to meters when you're actually doing the numbers, because if you want this to be in joules, you have to have the distance in meters. And so you can see that the energy actually goes down by a factor of 4. This is 1/4 of E total. Right. So it went down by a factor of, or it went down to 1/4 of what it was. Now, where did the energy go if we did this for an oscillator that was not damped? Of course, every time we go back to the top, we should have the same amplitude, therefore we should have the same energy. And you could convert to kinetic, but you're always going to get it all back. But we can see that when we convert to kinetic, because of this other drag force, this is not a conservative force, right? It always opposes the velocity. So it's not a conservative force, it's friction. And so all the energy is lost to, this much energy is lost to friction. Right? And of course, because the amplitude is never going to go to 0, the energy is never going to go to 0, and so we're never going to get all the energy out of it. But, you know, that's just how it works. Does that make sense? What I was going to say, though, which you don't need to know for this problem, doesn't require because they tell you the amplitude. But if you wanted to know the energy lost after time t, and they give you a time, and they don't tell you what the amplitude was, we could just plug in this, a0 e to the minus alpha t over tau, and plug in that time, and just plug that in for the amplitude, because that's the amplitude at any point. So
Would you have to account for if it's not at the max amplitude at that time?
you
So it'd be moving.
Oh, yes, sorry, you're right. So of course, okay, no. So you're right that if I just tell you a time, it's probably not going to be just happen to be at the top. If I tell you and it happens to be at the middle, but the energy at that point when it's moving and has some kinetic energy is actually the same as if it was all with this amplitude. So you can pretend that it was at the max and it actually has the same energy.
Okay.
So that's actually a really good point because yeah, you're right that it's kind of cheating to say at some point I'm going to just take this form for the energy because at that point it might not all be potential. I guess in this case it would because they told you it was exactly after 6 oscillations. But yeah, you're right. But yes, but this is always correct for just any time if you pretend it still has an amplitude at that time.
Yeah.
Okay, you see what I mean? Yeah. Right. Okay, that's interesting. I didn't think about that. Yeah. Okay. Does anyone have any questions about this? So there's many. I went around. This is just supposed to be like as long as you know all the pieces, that's what's really important. I think putting them together shouldn't be that difficult. But if you don't know some of the pieces, and here's just all the pieces in different. Of course, there's many parts. Like you could do this part first. That's fine. But yeah.
Okay. All right. So problem 7.3. I don't know if there's much of a physics explanation we need. It's just plug in the two formulas and try to prove that they equal this in time.
Yes.
All right. So in this case, for n equals 1, 2, and 3, do you just want us to like prove that it equals that in when n equals 1, 2, and 3, or?
Right. So
because I don't understand if it was a sum of n, but since n is an individual, does that mean that Fn has to equal the same thing at 1, 2, and 3?
let me. I think the. I think the crux of it comes down to yeah. So they give you something that has, no, I'm not going to write the whole thing. It's something like sine kx. Okay, there's much other stuff. It's a function of time. It's all this, but they give this, and they essentially, when you want to find when it's 0, right? And yeah. So this might be, for example, an example where this is the case is if you have a wave that's oscillating and it has like endpoints, right? So actually, this was. I think I did this in the first one of the math review things, which I don't know who was there for, but if this is a length L, this is like a standing wave, right? If you have a string, let's say with a length L, and you want it to vibrate or whatever, you can give it there's some time dependence, that's fine, but the spatial dependence has this, you can say it has this form. I'll just call it y of x equals a times sine kx, right? And you need that at x equals 0, it's 0. Now that's all automatically true by sine. If I wrote cosine, I could like do this, plus b cosine. But of course, at x equals 0, if I plug it in, this gives me b. This gives me 0, and of course I need y of 0 to be 0 because the height, like it's fixed at this point, so it has to be 0. So therefore, you can't have any cosines because cosines don't vanish at 0. Right, so that's just if you had this part. But they already have this. We also need y of L to be 0, right? And therefore, now that's actually not, of course, automatic by any of this. So if we plug in x equals L, that's because this is x, we get a sine k times L has to be 0. And now, of course, divide everything by a, that goes away. And now this is not obvious either. This is a number. K is a number and L is a number. So this is a number. Of sine of that number is 0. Now, sine of things are not usually 0, right? Only sines of specific things are 0. And so we know that KL must be one of the things that sine of it is 0. And we can actually write all of the things that sine of it is 0 in this form, n pi, for n is integer. This means is an integer. It means it's an element of the set of integers. I don't know how often they'll use this, but this is, anyway. So if n is any integer, n pi, sine of n pi is 0. and that's actually all of them. You can't just like make up a few of them. You can't just list a few and say, because it could be any, right? Any of the, you want actually get all of the solutions to this thing. So all of the solutions are the ones where KL is n pi. And now, therefore, we can actually solve for k as a function of the other things. Now, k is like actually it's the wave number. It's not the spring constant this time. But so if we write k as n pi over L, I'm just solving for k, then the solutions become y of x is a, still don't know anything about a because it canceled, sine of n pi x over L. Okay, now this has an n in it, right there. So, and remember I said that n could be any integer. Any integer solves this thing. So if I plug in any integer, it's a wave that vanishes at 0 and vanishes at L. That's literally the only requirements we gave it, right? And so if I plug in any n, it will still work, but it won't be the same. Of course, it's not the same function. It'll be different functions. And I think I forgot what the problem was about, but this is definitely relevant. I'm not just going off, but
Basically, you want to plug a formula into another formula and show that it equals the third formula in the textbook. And then we have to prove that it works at n equals 1, 2, and 3, which you just...
yeah, that's a little weird. I
It
guess
is a
you
little
could
strange.
explicitly do it.
Yeah, you could just prove that at 1, 2, and 3, it's not equal to 0.
At 1, 2, and at n equals 1, 2, and 3,
Yeah.
it should be 0 at x equals L,
Okay.
and at x equals 0. Well, so if I plug in n equals, first of all, if I plug in n equals 0, it's flat, right? Sine of 0 is 0, and literally the function is 0. That actually satisfies all my properties. So that's actually a totally fine solution. It's the solution where nothing happens, which in mathematics is mostly a solution to most problems. But it's not a very interesting one. So if I plug in n equals 1, then I get pi x over L. I mean, like you could graph it if you want. I'll just say it's going to be like this. It's going to be the sine wave where the first time it goes to 0 is when it gets to the end. So you could have this wave, and of course, if it has a time component, so I just took the x component, my whole wave could have been. Now it's going to be times, cosine of omega t or whatever, right? That's this is just another time component. You could also write it in here if you want with some simple rules, but I'm just saying this could be so this is really oscillating in time, but it's completely separate from the x component. And if n equals 2, you're actually going to get something like this, right? Of course, if it's oscillating in time, it's going to be like going up and down. Because n equals 1. This n equals 1 is called the, what is it called? I forgot what it's called actually. The fundamental, that's what it's called. The fundamental frequency. The fundamental frequency is the lowest one. It's one where, like, it couldn't possibly be any lower frequency because then it wouldn't, it could be 0, but doesn't count. And the first one like this, where it's n equals 2 here, is this one, and n equals 1 is this one. The dotted line is just the other side of because if it's oscillating up and down, you'll see both sides. N equals 2 is called the first harmonic, usually. The harmonic frequencies are the ones where it still satisfies it, but you have other nodes in the middle. So there's sort of an additional condition kind of thing, that there's 0 in the middle or whatever. And then, of course, you could have 3 of these, right? It would be like 1.5 sine waves. That would be n equals 3, n equals 4. Of course, at any integer, n equals 1,000 or whatever, it would just have like a bunch of little lumps, and then it would go to 0 at the end. And there's infinitely many, but you can't have just any. So these are the frequencies, right? They're called the wave numbers. K is the wave number. All right, K is. This is just the name. It doesn't really It's just the thing. It's just like the omega is the frequency because it multiplies time. K multiplies x, and so it's like this frequency in space. So omega is like, it's 2 pi. Well, okay, I won't say anything about 2 pi, but it's like the frequency in time. K is the frequency in space. So a higher wave number. So this thing here is the wave number multiplied K. The higher wave number means it's more frequent in space. It's sort of higher frequency, over this thing. Now this could be a string. this is how like violins work or whatever, or pianos or whatever it's a string, and the endpoints of course are fixed because that's required. And you get, you pluck it or whatever, and it vibrates in a series of these oscillations, right? It doesn't vibrate in just one at a time. It could, that's possible. It usually doesn't. But in these series, and then of course, any wave that is zero at the endpoints, or any wave that's, any wave that's zero on the endpoints, that no matter how crazy it looks, can be written as the sum of these types of waves, which is the whole Fourier thing, which we don't have to get into, but
Okay.
Even if it wasn't fixed, you could write it as a series of sines and cosines, but anyway.
What about Chapter 7, Problem 1? Honestly, looking at this, it doesn't look like it's a problem that really requires conceptual explanation so much as just studying what actually goes into the formula for a wave.
That's a good, so I did look at this one, so okay, I'm gonna erase this, so that's okay. So this one involves, the actual problem is just pretty much simple plugging in, I think, but I just wanted to make sure you knew what these standing waves were. You could also have standing waves, you don't have to have them fixed at the endpoints like I've drawn. You could have other conditions like have it be open at the endpoints, and that would just be a different condition. So depending on what the wave looks like, for fixed at the endpoints, it's like a string. But like if it's open at both ends, you could have like a flute or whatever. I don't know how flutes work really. I think that's pretty close. I think it's like, well, anyway, I don't really know. Okay. Anyway, you could have different, depending on the different conditions, you have different types of standing waves, and you would have to like, whatever. So, what was I going to say about this one? Right. So they give you, it's like a. So they give you y of x and t is a sine. I'm really sick of waves already. T plus phi. Okay. Whatever. So it's a. So that was the thing I said like a while ago. I said before we started. I said there's a simpler way to see waves than this one, and the other one is they actually write it a few times in the book, but it looks like this. I'm not going to write a because that's actually not a anymore.
You don't like A's, do you?
Not really.
Thank you.
Cosine omega t. So these are not equal, so don't write that they're equal. There's some factors and there's some other things. This is actually, I think, a much easier way to see things, because this is like you have at some fixed time, you have something that's a wave in space. If you plot it over x, you'll see it as a wave at some fixed time. Then if you take it some fixed space, this is a constant, and you'll see it's oscillating in time. So this is actually much easier to see that it's a wave. It's oscillating in both space and time. If you fix one of them, fix means set the time or the space to be a constant, you'll see it's a wave.
So, if they're not equal to each other, but they're both waves, what are the differences?
I don't remember. You have to look. They have the same information. What I just mean is that there's a thing that's like sine of a plus b is like sine a cosine b minus sine b cosine a. I don't know, something like that. Something like this. You just have to. It's a thing that's annoying to write.
Okay.
I wouldn't try to write things like this usually, just because anyway. The point is that it's the identical information, right? The information of if you fix one of these, actually, it's not really that hard to see, I guess. If you fix one of these, if you fix omega t, if you fix t, the time, the omega t becomes just a phase. So you get a thing in space, and if you fix the other thing, it becomes, so it's the same information, I guess. It's just, I don't know, I kind of like this better because it looks like definitely a wave. Well, I guess it's the same information. Anyway, but the sign is the thing that's really hard to figure out because I believe if it's a minus sign, it's moving to the right.
It says that explicitly.
Yes, it should say that because it's kind of hard to, to figure that out, what you could do is stare at it for a while. And then when I say stare at it, I mean, think about, well, what if I set t to be something small? So if I set t to be 0 and then t goes to something small, if t moves forward in time, I want to see where the wave goes at some fixed x position. If it goes if it was 0, then it goes up, that means that the sine wave is moving, see what I mean? We have to stare at it for a while. It won't help much if I explain it. And also, it'll take a few minutes for me to actually think of it. But if you stare at this for a while, you should be able to kind of visualize, for a very small amount, what the shape of the wave should look like. And then if you go a little forward in time, does it look like this, or does it look like this, right? If it looks like this, it means it's going to the right. If it looks like this, it means it's going to the left. So if you play with some small values, you should be able to visualize which is which. Or you could look it up in the book and it says.
Okay.
I mean, you should verify it, but I believe if it's a minus sign, it means it's going to the right. And so they ask you to verify that. They ask you about the wave number. The wave number, as I said, is just like the frequency, but over space. So it's the spatial frequency. That's actually a better way to talk about it as the spatial frequency. The angular frequency is just the time frequency. We already know about that. It's not like radical k over m or anything like that. That's last chapter. This is a new thing. This is just omega is now a new variable that's just a time. In time, at some fixed position, how is it oscillating in time? The phase
Phase is just a question of where it is on the graph, like if it's been translated to the left side or to the right side.
yes, at t equals 0 and at x equals 0.
Okay.
If the value of the wave at t equals 0 and x equals 0 is 0, then of course phi is 0. Because if you plug in 0, 0, you get a sine of phi, and of course if this is 0, it's already done. If it's like 1 or whatever, you'd have to solve for phi. It would be something kind of complicated. But now the speed of the wave, they probably say something in here about how to find the speed. It's like some formula with the.
You could do. 'Cause
Really?
I was going to ask you, when you take the derivative, are you supposed to take it with respect to both x and t?
Which derivative?
Oh, I don't know.
I think that would be the root of the the question. So that's a good question. So when they say what's the transverse velocity, so what the wave is doing. So if we look at this is y, and this is going to be x. Okay. So this is in space. So remember again, this wave function is over a spatial distance. It's oscillating, but it's also oscillating in forward in time. So when you draw it like y over x, of course, this is all at t equals, let's say, 0. Okay? So this is at a fixed time. Now, at t equals, let's say so this line will be at t equals 0, and this dotted line will be at t equals epsilon. Epsilon just means a small number. So I'm just saying a little bit later. So a little bit later, we should have something like this, right? Where the wave just started to decrease, and then it's eventually going to go to 0 and going to kind of go the other way, right? Actually, sorry. Well, sorry, that's not true. It's going to go. Oh wait. No, sorry, that's not what it's going to happen. It's going to go to the right. At t equals 0, it looks like this. At t equals some small number, it's going to go like this. Right, if it's moving to the right. And now what you'll notice is that at a given, let's say, I'll pick, and then this is going to go like that. So at a given x position, this is x naught, this is a fixed x position, right? What's actually happening? Well, the position, which is given by the y, like the actual position of each point on the wave, is going downward, right? And it's going downward in time. So at a fixed x position, there is some velocity going down and up, right? Every point on the wave is only going down and up. It's not going to the side, right? The wave is traveling to the right, but the points, if it's made of a substance, like a wire or whatever, the actual pieces of matter are going vertically. So the transverse velocity is the vertical component of the speed. Sorry, it's the speed. There's only a vertical component. Now the transverse velocity is, transverse is in the y direction, right? Transverse, because the wave is going this way. This is x. Y is transverse. It's really, I guess, up, but you know what I mean. Up and down is transverse. So the transverse velocity is going to be, remember, velocity is always with respect to time. So this is going to be the transverse velocity. Does that make sense?
So we take the derivative with respect to t of that equation.
Yes, exactly. And then you plug in a fixed k, which of course, if you plug in a fixed k, you're just going to get a phase. And you'll see that, of course, well, let's just do it. So you'll get a omega cosine, and then everything in here stays the same. I mean, you have to pick I'll pick minus. Just pick minus for now. Of course, you can't just leave it as plus. Well, you can't, because then, so it's actually a minus. Which makes sense. It's good that it's minus, because you can see the points are going down at the beginning. Of course, later they're going up because it oscillates. But anyway, omega t plus phi, okay. Sorry, I keep using phi here, phi, instead of delta, which is what I was using before. I don't know why. I just keep switching. So you get this. Now, of course, if we pick a given, let's just pick x naught. Sorry, let's pick x equals 0. Just why not? Well, if you pick x equals any fixed thing, you'll see this just becomes like a phase. And of course, the velocity, well, okay, it'll be different for each one. Okay, fair enough. I was going to say it doesn't matter, but it does matter a little bit. You just plug it in, and it would be some number. If you had an explicit expression with numbers for everything, you could just plug in all the numbers, right? Like if you have explicit, sorry, I shouldn't mean, if you have a k as an exact thing, you should be able to plug it in. And if you had the wave value at t equals 0 and x equals 0, you could find phi. So let's say the wave is 0 at 0, which is what I tried to draw there. So that's 0. This goes away, and now you get an actual. There is a real phase, so it's not like it's not a fake, ignorable phase. It's a real phase that you get, but it's just something, and I could plug in x naught. If I plug in x equals 0, then this would go away, and I'll get a omega cosine of minus omega t. Just side note that cosine of a negative number is cosine of a positive number. So it's an even function. Sine is not an even function. Sine of a negative number is negative sine of that number. Anyway, just fun little thing. So then you get a negative at x equals 0 and at t equals 0. You get a negative velocity, which makes sense because if the wave is moving to the right, the points are going downward at the beginning. Later, they're going up because, of course, if you go to later x positions, this cosine is going to eventually flip around. That's the whole point of these oscillating things. Anyway, sorry, what was the point? Oh yeah, this is the transverse velocities. The transverse velocity is the time derivative of the y position at a fixed x. It doesn't have an overall transverse velocity because each point has a different transverse velocity. Because, like for example, like this point going up, yeah. So like this point here didn't have any transverse velocity at some point, right? Because it was at the edge point kind of thing. Now right at the edge, it doesn't actually have 0 transverse velocity for a second. So anyway, you can see that they have different transverse velocity at each point. And then they say the transverse acceleration. Well, of course, that's just going to be this, right? It's just sort of the same word, transverse, so you know it means y. And acceleration would just mean the second derivative. So of course, we can just take two derivatives of that. You can't plug in x naught, of course, because otherwise it'll mess everything up. But well, in this case, it doesn't matter, but you know what I mean. Take two derivatives of it at a time and then plug in whatever. I should really put like a bar x naught for a transverse velocity at x naught. And this is, transverse acceleration. And so the speed of the wave. Okay, it's like k over omega or something. I don't know. It's like omega over k, yes. And now I'm just, well, so sure. Okay, it has to be, of course, because sorry, you're right. Because this is 1 over seconds and this is 1 over meters, so it has to be meters per seconds.
Or wavelength over t.
Or wavelength over t. That's actually, okay, thank you. That's a much better way to say it. That's not necessarily a better way because this you can solve directly from the formula. It's wavelength over t is a much better way to say it because what we mean by the speed of a wave, because when we say remember what I was just saying, the wave is moving, but like the points, none of the points are moving like the wave is moving. None of the points are going to the right. So what is actually moving to the right? We have to kind of like, it's not sort of obvious from like the level of like the matter of what's sort of going on. This is very obvious because you can just measure this directly. But how do you actually interpret the wave moving? Like, what do you actually supposed to measure? Well, we have a well-defined notion of the wavelength, right, which is this. And we have a well-defined notion of the period, which is if you look at a certain point in space, like let's say x equals 0, this point is going to go down and it's going to go up and then it's going to go back to 0. And that's one period, right? So it's at a certain, so this is at a fixed point in space, this is at a fixed point in time, but you have a well-defined notion of, you could actually make this graph for y over t at a fixed x if you want. That'd be really confusing, but I'm not going to do that. It's already pretty confusing because we have, I'm drawing on a board where we actually have 3 variables. We have the height and then we have x and t. So anyway, it's already a little confusing, but yeah, so the wavelength we could write in terms of the wave number. The wavelength is actually 2 pi over the wave number. Okay, because the wave number, remember, we could do the units thing again, where the wave number is like after 2 pi wave numbers. It's not a very good way to. Trying to think of how 2 pi. Anyway, here we go. I'm just trying to think. It's the same relation as the omega to the period. Right, so the omega, like the 2, because the other thing I was talking about how the 2 pi's have to cancel. The 2 pi has to cancel. This is 2 pi radians per revolution. Okay, I see it. K is 2 pi radians per meter. It's a little tougher to think about. I would recommend just thinking about it in terms of an analogy, as in K is just like omega, as in. This is literally just in meters. It has nothing to do with radians at all, just like this. Whereas these do have to do with radians. You know they have to do with radians because there's no 2 pi's anywhere, and they just go in a sign. So they have to have radians in them, right? And so K is radians per meter, and we want it to be just 1 over meters, right? Or sorry, meters by itself. So if just like this is, we want this to be in seconds. This is radians per second. And we want to do 2 pi radians per cycle, and this is 2 pi radians per cycle as well. 2 pi is always radians per cycle. That's literally that's the only place, again, like I said before, the only place you ever use 2 pi anywhere is when it's radians per cycle. That's literally what it means. So whenever you see that, you can always kind of put those units in. Anyway, hopefully that's a good enough explanation. And you can see if you plug both of these into here, you'll get, if you plug both of these into here, this is sort of the intuitive definition of what we mean by the velocity of the wave. It's how long does it take to go through one wavelength, right? And we can convert to something that just has these variables in it if we want, which is these are the sort of the input variables of your wave function.
Okay.
So this is the speed of the wave. Does that make sense?
I think you got the bones of it.
Just keep in mind though, this is the transverse velocity. This is the speed of the particles vertically, which is the only way they're moving in the medium that makes the wave. The wave is separate, is like its own little thing that travels through a medium and is sort of an abstract thing that we can define with functions. This is the speed in the x direction.
Okay.
I mean, yeah, okay, yeah.
Quick question, because I have to go.
Yeah,
soon.
sure.
All right. You guys mind if I just comment? Okay. So number 2, it's basically taking this formula right here and putting it here, but it looks like all we have to do is just take amplitude k, x, omega, t, what we found right here, and just sub it in.
Yes.
All right. And then when it asks if it could also be written this way, I figure that the answer to this is just yes, except we would just have to take something into account such that the omega sign is such that the sign between the x and the omega is positive instead of negative. Like we can make this positive, we just have to find a way to compensate out here.
Yeah, I mean,
Like
It's
it
kind of a
could,
stupid question.
it could be done.
Because
Because just why would you? It's like making your own Kit Kats.
Yes, the only difference between what they write here and there is because there's no phase
Yeah.
here. But I think what they want you to do is because they write a tilde,
With the oh yeah.
and they write it inside the real, right? Real part of a tilde times da da da. Now, this is very suggestive of the fact that if it's inside the real, it's probably not real by itself. Because otherwise,
It's inside the real, it isn't real. Okay.
yeah, because otherwise, why would you take the real of it? It would just be like, the real part of a real number is just itself.
Oh, okay.
So why would you put it? I think what they mean is that this can be complex. So if you take a tilde to be the regular real amplitude a times e to the I phi, which is the phase, you can just have the amplitude with a phase.
Okay.
Sorry, I'm squishing it all down. But this is for the next problem. They ask if you could write it essentially in the same form we've had, but they have a key difference, which is that the phase is not part of the. It doesn't write it explicitly as where the phase is there, right? And I think what they want you to think is that why don't we just call the amplitude the new imaginary amplitude, because it's already imaginary in the
Okay.
exponential part. Why don't we just call this here?
And
Right?
so because of the rules of multiplying exponents, it works out the same as up here, right?
Yeah. Oh, yeah, yeah. If you write it out, yes, it would be
Okay,
the same.
okay,
Yeah.
so it works out. Number 7, I don't think there's anything you really need to teach on that. We could just as easily find
Oh,
a graphing program and just
7
type it
is.
in. I'm gonna guess
I
you don't-
looked at online to see if there was a solution,
Uh-huh.
which there isn't because whoever made the solutions is not on top of it because a bunch of them are wrong. But I looked online to see if I was missing. This is like very simple. You could just literally type this in Wolfram Alpha.
Yeah, that's what I
So
was thinking. Just
the-
a graphing program.
Yeah, the only thing you have to sort of figure out is that when they say two sine waves or whatever, two identical waves in the same direction, so let's say it's like this. And of course, when they say plot, you can't really plot it if it has 3 dimensions. So I assume they just mean at t equals 0, right? Write the plot. Now, if the plot is, at t equals 0, there's going to be sine of kx. Okay, so some wave moving to the right at t equals 0. If you pick some fixed time, okay, here's my train of thought. If they say plot it, they probably mean at a fixed time, and if they say at a fixed time, why are they telling you what direction it's moving? Whatever. So at some fixed time, the wave looks like a sine of kx, and if they say that plus an identical wave moving in the same direction with just a phase of 3 pi over 2, you could just write this as sine kx plus sine of kx plus 3 pi over 2. And then just say k to 1, doesn't really matter. Of course, if you plot it over, just make the scale whatever you want. If you just type this in, like, anywhere, like, probably Google will graph this for you. I don't even, if you type in Wolfram Alpha, it will just give you a plot, and it will just look like this. It won't be lined up with 0 or anything because it's sort of a weird thing. Now, of course, also you could note that this sine of this is cosine x. I believe it's just cosine. Actually, hold on, it might be minus cosine. I think it's plus cosine. It's either plus or minus cosine. So it's literally just plotting sine plus cosine. Or sine minus cosine. One of those two, I forgot. I think it's plus. Anyway, and if you just type that in somewhere, you'll just get, it'll look just like a sine wave. It won't look any different, right? Because we've seen that that like a sine plus b cosine solves all the wave equations. So we know it must be just a wave. So even though it looks like it's 2 waves, it's actually just 1. Right, we saw that those in the last homework. One of the questions said, show that these different forms solve the same wave equation. This is just another way to show it. Is that sine plus cosine is just a wave, just like sine of k plus phi or whatever, right? Kx plus phi. Anyway, you just plot it, and I guess that's the whole thing. I don't know what they could possibly want you to be doing. The fact that it's moving in time doesn't affect this because you can't plot a motion. I don't know. It's really weird. I guess you could plot it forward in time. It wouldn't really matter. It would just move to the right, just like they said it would. So anyway, it's just, and they don't give you parameters. It's a stupid problem. So just plot sine plus cosine or something like that. Or just sine plus x plus 3 pi over 2. That's even better. You don't even have to do any like trig things. Like those are both totally valid answers. So I don't know what, you know, basically don't overthink this one.
Okay. I gotta run right now. Is there any? Sorry. I think that's pretty much the entire homework, though.
Yeah.
I mean, like half of it was just stuff you got to look up on your own, or just plug into Wolfram Alpha.
Yes, there's some like especially that number 1 in this chapter would just ask you like every single variable. I would definitely like really look those up all the book. I know you're obviously going to anyway, but just like especially that one, like it is really important that you at least know what all the variables mean because there's a lot of them in this chapter.
Okay. Let's see.
There's actually fewer variables when we do quantum mechanics. So
Well, yeah, but
that's actually sort of easier.
But don't
in
those
some
variables have an inherent uncertainty to them?
You'll see. I don't want to ruin the surprise.
The surprise is that there is no surprise. The surprise
to
is
you.
also in a state of uncertainty. All right. Thanks for your help, Keegan.
Yes.
As always.
Does anyone else have any questions about any of these or any other things you want me to talk about?
You kind of lost me on 2.
2, yeah, what was 2 again? Oh, I didn't really say much. Yeah, I sort of said it very quickly. So that was, thanks. Yeah.
We'll talk tomorrow.
Um,
Have a good one.
yeah, so the only difference between, sorry, it's not far enough out there. The only difference between writing it in that sine form and writing it in the real part of the imaginary exponential form, just like with the harmonic oscillator in that problem, you could write it either way. But if you write it as, so I'll say a sine, okay, this, and they write it as RE A,
What do you call that thing?
which one?
The squiggly thing?
Oh, tilde. Tilde, it's tilde.
Squiggly.
Or squiggles. My I had
That one better.
my topology teacher when I was an undergrad called it squiggles.
Oh,
So I kind of like that. She was Russian, and I don't know if it's like they actually call it squig, like if they use the translation of the word squiggles in Russia. I don't know. But anyway, yeah, it's called a tilde. It doesn't mean anything on its own, so don't like. It's not like
right, it's just like bar or whatever.
right. But so what I was going to say is like if they write a complex number with a bar,
Oh,
that means
that's
complex conjugate. But squiggles, they don't, you're not supposed to know what it means.
It's
so-
just a different indication.
Exactly. In this book, they tend to use it when something is complex. Similar to the bar. Well, the bar would be a specific thing. They tend to mean it's a complex number, but not always. So you could probably safely assume that in this book. But anyway, yeah, so they want to write this in this form. Well, remember that now we did this, there was a similar problem on the last homework without the wave part, without the t part. And remember that real part of A, now let's just pretend that A is real for now. This would just be, the real part of this is cosine of whatever this is. Doesn't matter what this is, right? Sorry, they use a minus in the first part. That's this, right? So if we want this to be, so this is this, but of course we have a sine. But of course you can replace this. This is equal to a cosine. We could just replace it with a cosine, but of course then we have something like that. It might be minus actually.
What?
Yeah, no good.
What happens to our phase shift?
Yes, that's. I'll get to that. That's the main thing they want you to notice. I just remembered that this is a thing too, because the real part, of course, is the cosine part. So we could shift this is equal to this. Now these are identical wave functions. There's no change of anything. It's literally just these are identical. It might be a minus here. I don't remember. It's one of those two. Anyway, but it's just shifting between sine and cosine. Therefore, this is the same as this, but of course, we also have this thing here, the phase, right? This is not going to be, if we take the real part of this, it's here. So what can we do? Well, we can just say, well, what if this A tilde is equal to A times e to, now of course, exponential of, AB is e to the, sorry, that's not what I meant. Right, this is just a thing about exponentials, right? E to the A plus B is EA, EB. So we could write this as e to the I phi plus pi over 2. If we wrote A tilde as this, then we would get, I'm losing track of what I'm talking about now. Then, if we plug in everything inside RE with this, right, we get A e to the I phi plus pi over 2 times e to the I kx minus omega t. And of course, this and this are exactly the same. Right? Sorry, well then we take the real part, but then it's the same. Right? Take the real part and we get exactly this. So this is the substitution we have to do. So that second form meaning the one with the real part of the exponential thing, if we would just replace A squiggles with the regular A, which is a real number, times this imaginary exponential, which just has the phase in it, and it also has the phase shift to get us to cosine. Now, if we change RE to IM for the imaginary part, we wouldn't have to do this phase shift because the imaginary part of an exponential, complex exponential is sine. So, that's just a subtle thing, but we don't. If you forget this on the homework, I'm not going to care that much. Because there's already a phi. You could just define phi prime to be this quantity. I feel like, I hope everyone's gathered that phase shifts don't really mean anything. They're very, very,
It's like your initial conditions.
Exactly, but for the dynamics, most people don't really care about that. I mean, to do problems, you need it.
Mm-hmm.
But for something like this, I think they want you to figure out that, what if I just change my amplitude, which used to be, now an amplitude is a number that tells you how high the wave goes, right? This number here is a complex number. That can't possibly tell you how high anything goes because it's not a real number, right? So it's something different, but that's fine. We can sort of expand, just like how we used to be talking about waves just traveling, and somehow now we're talking about complex numbers. Like, it seems like we went way too far. But it's fine as long as we, at the very end, our wave function is a real number. So just like as long as, we can't quite call this the amplitude, but this is some number, and then when we take the real part of this whole thing, we still get a real number, and all the information is here, right? It's just sort of reshuffled a little bit. So I think the moral of this is that don't be too scared of imaginary numbers. But of course, when you do any real calculations or when you get any real answers for things like measurements like meters and time and frequency, they of course have to be real numbers because the world is made of real numbers. But we can do all the math with imaginary numbers, like things like this. So anyway.
So when they're asking for the values and signs of A tilde, K, and omega,
Yeah.
it's we know omega is.
Yeah, the second one, they switched the sign in here.
Yeah.
I think you can just say, there omega is negative now.
Right.
I don't see what the...
But
yeah.
your K and your A tilde are going to stay the same.
Yes, they
sign.
should.
Okay.
Right, because it's the same wave, it's just going the other direction.
Okay.
You could think of it like the time evolution is running backwards. That's maybe not a helpful way to think of it, but you could also think of it as, the wave is the same, but instead of running forward in time, it's running backward in time, but of course, a right-moving wave moving backward in time is just a left-moving wave. So that's what the sign means. If you replace t with minus t, this just means running something backward in time. And so you could do this for a variety of our physics equations for the whole semester. If you do this, you can get something else that's equivalent to something running backward in time. That's a little more philosophical than I wanted it to sound, but anyway. But of course, that's the equivalent to replacing this with a different sign. Does that make it more clear? Okay. Yeah, if you write everything out, I would just write out A tilde, plug in this thing. If you write it all out and then you combine the exponentials, it should be you get identical things. If try to make too many leaps in your head, which is what I tend to do sometimes here. And I'm trying to get better at writing everything down. But if you make too many leaps in your head, you start to like lose track of all the leaps, I think. So that's probably what I was not doing very well. But yeah, if you write it all out, you should get identical things. You'd be like, okay, well, they perfectly match. I only made these identifications like this, and therefore this is the sort of answer or whatever. So, okay. Any other questions? Okay. All right. This is probably the least fun homework, in my opinion. So if you're not having a lot of fun, it'll get more fun, I think.